Good morning, good afternoon, and good evening for those of you joining us today from around the world. My name is Allison Douglas, Market Development Manager at Agile Technologies, and I'll be your host for today's webcast entitled Analyze Agile or Elusive Signals Using Real-Time Measurement and Triggering. This webcast is a third in a series aimed at educating customers on the fundamentals of RF and microwave measurements. Last month, we focused on basic signal analysis techniques, and today we will focus on capturing and analyzing more complex intermittent signals. Joining us today is Ben Zarlingo. Ben is an application specialist for Agile Technologies' signal analysis operation. He is primarily focused on signal analysis at RF through millimeter frequencies, including the characterization of wideband and digitally modulated signals and optimizing measurements for sensitivity and low noise. We'll begin today's webcast in just a moment, but first a little bit about the process. Ben will answer questions at the end of his presentation today. To participate in the Q&A session, you can enter questions at any time during this presentation in the question window on the lower right-hand side of your window. Be sure to address your questions directly to all panelists by clicking on the pull-down menu. We have a lot of people online with us today, so I apologize in advance if we don't get to all of your questions. But don't worry if we run out of time, we will respond to the remaining questions via email. We will also email you a link when the on-demand version is ready to view, along with a copy of the slides presented today. We also ask that you take a moment to fill out the short feedback form that will appear when you close your WebEx session. Now let's move on to the presentation. Welcome, Ben. You now have the floor.
Well, thanks very much, Allison, and good morning, everyone. Thanks for attending our webcast today. Hopefully this will be useful information to you, extending from some principles that some will call basic to some that are significantly more advanced, and spanning from traditional swept spectrum analysis through some of the more recent technologies and capabilities. So let's get right into a summary of our presentation today. We'll be focusing on agile and elusive signals, or in some cases signal environments, and we'll be splitting the presentation in a couple of major pieces or a couple of topics, one of them being discovering these signals or the behavior of these environments, and the other piece being the more traditional engineering jobs of troubleshooting and optimizing either the signal environments or the hardware, or in some cases today, software as well. For convenience and clarity, I'll do that around a couple of case studies, one of them being a fairly dynamic signal environment, one of the ISM bands. The other example we'll use is a radar signal. And we'll focus mostly on the processes of choosing and using different test techniques and tools. In particular, I want to spend some time making the most of the kinds of tools that you already own and the kind of knowledge that you already have of your circuit, of your system, or of the signal environment you're dealing with. A great deal can be done with the instruments and software already in your lab in many cases, and so I'll talk about making the most of that and leveraging that to additional software or hardware capabilities for some specialized analysis. So we will certainly cover swept spectrum analyzers, vector signal analyzers, and a little bit about oscilloscopes, along with one of the more recent tools, the real-time analyzers. And toward the end of the session, I'll talk about using triggering to enhance measurements, though I'll discuss some other trigger techniques during the presentation itself. So let's get right to case study number one, the 2.45 gigahertz ISM band. In most parts of the world, this band is about 100 megahertz wide, centered at 2.45 gigahertz. ISM stands for industrial, scientific, and medical, though in many parts of the world that band is largely used these days by wireless connectivity applications, wireless LANs, Bluetooth, cordless phones, things like that. The band typically uses the signals in the band typically use some sort of spread spectrum technique. In some cases, that's compulsory. However, it's a fairly lightly regulated band. If you meet the requirements of the band, you can use it no matter who you are. And that does create some complexity from the standpoint of signals that interfere with each other because the signals are not explicitly coordinated. So we've talked a little bit about some of the users already in terms of things like wireless LANs, but one of the issues in this band is powerful other users such as microwave ovens. Many of them operate in a frequency inside this band at fairly high power, and even with good shielding they do emit some signals that have considerable potential to interfere. As I mentioned earlier on, this band is quite dynamic, and so for that reason we don't typically know the content of the band at any specific point in time. Signals may be very low duty cycle. The band may be low occupancy. So there are some interesting potential behaviors here that make it a good test case for the kind of thing we'll talk about today. And as I'll describe a little bit later, effective use of this band means avoiding a certain degree of crowding. At some degree of crowding, this band can become much less functional. And if those of you who've operated in wireless LAN environments where there are many users are probably already aware of that. Well, let's take a look at the kind of view of this 100 megahertz band that we would see using a swept spectrum analyzer. Here again, the band is 100 megahertz wide. We're looking at an example frequency span of 160 megahertz. And at the upper left, we can see the results of a single sweep from a swept spectrum analyzer. We may or may not catch signals, and they may or may not appear in their accurate form, because of course the signal is in many cases coming or going or in motion, and the analyzer's swept resolution bandwidth filter is as well. One of the traditional techniques to improve that kind of measurement is to use peak hold on a swept spectrum analyzer. And in this case, over a short interval of time, peak hold does reveal several things, one of them being the three main wireless LAN channels here, beacons or channel scanning in some cases, but we don't see very much else, and we see kind of anomalous behavior here on one of these channels. Extending the length of a peak hold measurement does improve the view in some ways. It shows occupancy of the band as a fairly well-defined thing, and we can see some ripples at the higher frequency range here, but it's difficult to tell very much about what's going on because some of these wireless LAN signals and some of their channel scanning has obscured some of the other signals that are part of the band as well. So there are really a couple of dynamics here, dynamics of the signal itself, and in a swept analyzer, then there's the swept resolution bandwidth filter as well. So this traditional technique is useful, but fairly limited in an active multi-user frequency environment like this. If we jump directly to one of the more recent types of signal analysis from a real-time signal analyzer, this color-coded display shows us a great deal about the signal in a very short time, in many cases in a single display update. The reason it can do that, the primary reason, is that it's processing a very large number of spectra per second, in many cases then being gap-free over the band we're talking about. This means that no signals are missed during that band, and we encode the signal, in this case, in what's sometimes called a histogram or density display, where for each pixel on the display, the more frequently that pixel is hit by a measurement result, the color changes on that from blue on up through yellow or red, and you can see that color encoding on the right-hand side of the screen. You may already be aware of real-time analyzers and these density or histogram or cumulative history or DPX. There are quite a number of different terms for this display. But in any case, we can see the three wireless LAN channels. We can see some different shapes here. We can actually see signals inside of other signals in some cases. And then we can see some narrower band tones here as well. So this is a fast way to get insight into what's going on in the display. In many cases, the analyzers will put up, say, 30 or so of these displays per second, each one of which represents thousands of spectra. So that gives a very good intuitive feel for what's going on in the signal band, good for signal discovery. Another way to use that large amount of spectrum data is shown in the bottom of the display here, and that is a spectrogram where we add a time axis to the signal. The problem with the frequency, with the density display in the previous slide is that it does tell us what happens over each display update, but it doesn't give us any indication of how the signal changes or evolves over time. So one way we can change this is to use a spectrogram where each raster line or each pixel line of the display represents one spectrum result, as you'd see in the top part of the picture here, and then we stack these on top of each other over time. And in this case, then, we can see the wireless LAN signals here as the three large vertical bands. We can also see another signal that came and went, some sort of TDMA or TDD signal, perhaps a cordless telephone. And then we can see what look like some multitones here in several different frequency patterns. What this actually is Bluetooth. We'll show that a little bit later in the next slide. So the spectrogram has the advantage of combining together a large number of combined spectral results, each one of which is thousands of spectra. Over a period of some seconds in this case, we can see how the frequency band is occupied. So that is another additional view in addition to the density or histogram display. Let's go ahead and change that display slightly. In this case, the same settings, except that we have changed the frequency acquisition time. That is, we've changed what chunk of time we combine spectra from. The real-time analyzer in this case is calculating almost 300,000 spectra per second, and we can only display or update the display about 30 times per second. At least that's as much as a human can see, and so we need a way to combine those spectra. So that's the acquisition time setting here. And if we set that to one display update, we have the trace we saw previously. But if we want better resolution in time, that is, we want narrower time samples, we can switch this down to 1 millisecond as a frequency acquisition time. We can go to lower values than this, but in this case, going to 1 millisecond begins to reveal these wireless LAN beacons, some channel scanning, and we can start to see something of these individual Bluetooth hops. We can see that those signals that appeared to be a line spectrum or vertical bars in the frequency in the previous display are actually shorter bursts. We can, of course, use a marker on this spectrogram display to look at individual traces, individual spectral traces, as we would see on the top. So this has the advantage of finer time resolution. It has the disadvantage of covering a shorter distance in time. So our update rate or our spectrums are 30 times faster in this case in terms of the display updates. That means we do 30 of them per screen update instead of one, and in this case then a few thousand spectra or a few hundred spectra for each one of these displays. So we're trading off time, the time span versus the time resolution. So we've talked a little bit about the displays of real-time analyzers. I did want to spend a minute or two discussing real-time analyzers themselves. Some of this may be new to you if you haven't been using the real-time analyzers yet. The main and perhaps most obvious characteristic of the real-time analyzers is a way to create fast display updates, and for each display update, a high density of data. That is because we're getting hundreds of thousands of spectra per second. Each display needs to represent a large amount of data. They really are good for easily understanding a signal or the frequency of an event. And they're especially powerful. Probably the single biggest contribution in practical measurements is finding very infrequent events. Since they calculate large numbers of spectra and generally operate on a real-time or gap-free basis, they allow us to find and to reveal very infrequent events, or equivalently to find unexpected events or signal behavior. So they're very powerful in these ways. They do have some limitations as well, and that's why they're often used in combination with other analyzer types. They do combine traces from different times, so they have some limits in terms of their time resolution. They also, because of their FFT speed done in hardware, have limited measurement flexibility in terms of combinations of resolution and span. And that sets them apart a little bit from traditional swept spectrum analyzers, one of the reasons why they tend to make sense together. There's usually some sort of limited frequency span. That is, if you're going to remain in real time, you need to be processing all of the data that comes in, and that typically is some sort of limited span. The widest of those spans these days is about 160 megahertz in the Agile PXA series signal analyzers. They also, for various reasons, calculate power spectrum only, that is, frequency versus amplitude. They are not generally vector signal analyzers. Let's go on and talk about real-time itself. I've used the term real-time, but haven't done very much yet to explain precisely what real-time is. Real-time has several different usages, but generally speaking, a good definition of real-time analysis is that it's measurement operations where all of the signal samples from a digital Iaf of a signal analyzer are used in calculating some sort of measurement results. That kind of measurement is usually spectrum, but there are alternatives to that as well. So that's a good way to summarize real-time. If you're processing all of the samples that came in either continuously over long periods of time or for defined shorter periods of time, things like time capture, that's real-time analysis. That leads directly to a term that's also in common usage, that is the real-time bandwidth. As you can imagine, the wider the bandwidth that you're operating with, the faster sampling you're doing, and at some point the fast sampling fills the ability of the real-time processor to do spectrum. So that is then the widest bandwidth where the analyzer can remain in real-time operation, either continuously or through a capture. So the current usage we've talked about in the previous slide for signal analyzers is typically a spectrum or FFT analyzer with a processing path that either processes all of the data for spectrum or other displays or processes that data for triggering signals, the frequency mass trigger that we'll talk about coming up. Here's a schematic diagram to represent real-time operation, and that is the T's here are time records, FFT time records, and the block at the bottom represents the calculation for the results from the FFT time record. If you are sampling fairly slowly and calculating quickly, then the calculation interval is much shorter than the time record length, and you're in real time. The same goes true as you widen your analysis bandwidth. At some point, the duration of acquiring a data time record, T1, T2, T3, is the same as the time to calculate those results and update the displays, and that's when we've reached the real-time bandwidth limit. If we sample even wider for a given calculation speed, if we sample wider, then the time records fill more quickly, and we are not in real time. There are gaps in the analysis here. There are some additional wrinkles in this. Even when we are doing real-time processing, we may effectively lose some data, and that's because of a phenomenon called windowing. That's shown on the next slide here, where we have different amounts of overlap. In the case of a narrower frequency span and fast calculations, we calculate much faster than it takes to acquire new data. So we can stagger these calculations or do successive calculations and simply add new data to a circular buffer for our time records each time. So this gives us what's called overlap processing, and that has a number of benefits. In FFTs, very often we use some sort of windowing function to create a resolution bandwidth and also to make the signal periodic in the window to give us good dynamic range. So in these cases, this window may weight downward or to smaller values the signal at the beginning and the end of the time record, and that can, without overlap processing, that can cause us to inadequately measure some data samples. So faster processing is always better in these cases. In most cases, overlap processing, if available, is a desirable thing. That does lead then to one of the issues that comes up, and I will treat informally here today, and that is probability of intercept, or POI. There are, in the surveillance and signal monitoring worlds and in some other disciplines, very rigorous definitions of probability of intercept. In speaking in terms of normal test and measurement, I think it's better to come with to use a more general treatment, a more informal treatment of probability intercept, and that is that high probability of intercept means that you can find the signals or signal behavior that's important to you, whether it's expected or unexpected, and that you can do that with a reasonable amount of time and effort. That is the core, really, of real-time or of probability of intercept for the majority of our electrical test and measurement world. That also means then that you can find and measure the signals as necessary. That does not mean that you can measure the signal perfectly or necessarily to the maximum accuracy of a signal analyzer. That may not be as important to you in many cases as simply discovering that behavior. A more rigorous treatment of this, especially in the context of real-time analyzers, is available in an upcoming micro app at the IMS MTT 2013 symposium in Seattle in June. A version of that is also available from Agilent's Aerospace Defense Symposium presentations that's happened in some cases already this year. The main thing then is probability of intercept is finding the signals or the signal behavior you want with reasonable speed and efficiency, and that of course those factors depend on your particular requirements. One of the elements of that I've briefly mentioned so far is frequency mass triggering. This is a type of triggering that takes advantage of the fast FFTs in a real-time analyzer. The display shown here is a frequency mass trigger display in the upper right and the configuration of the frequency mass trigger in the rest of this display. So in this case we can see the upper frequency mask in terms of the green mask with the green circles. That's the frequency mask we've chosen here, starting by building a mask from the trace itself and then moving that around, moving those points around. So that can be done in a graphical way, or it could be done in a tabular way as we see on the left. It can be done as an upper mask or a lower mask or both, and you can use some logic analyzer style criteria in the frequency mask in terms of entering the mask or leaving the mask and then entered, etc. But the frequency mask trigger is just what it sounds. It's a trigger based on a frequency mask or spectrum behavior, in particular power spectrum behavior. It's a fairly powerful approach if the signal you want to trigger on is not the only signal, if it's not the largest signal in the display, but if you want to trigger on individual frequency behavior characteristics. This is a powerful technique, though it has a couple of limitations. In particular, it is not time-aligned with the signal. So your time resolution for the trigger is limited to something related to the FFT period itself, or how often your frequency spectra are calculated. This trigger then, as we'll show in the presentation today, can be used to trigger a single measurement or group of measurements, or it can be used to trigger a time capture, the capture of gap-free data. And that can be very powerful in some ways we'll show in the presentation today. This is all based on a digital IF version of a swept spectrum analyzer structure, the super heterodyne down conversion that's been used at least since the 1960s in signal analyzers. In recent years, the IF processing has been converted from analog processing to digital signal processing in things like ASICs and FPGAs. And then the additional steps here for vector signal analysis, something that's been around for a couple of decades now actually, is piping this data into capture memory and into other measurements, sometimes fed from that capture memory itself. So better than talking about the architecture here or the block diagram, we'll talk about some of the measurements that make vector signal analysis a good complement to real-time analysis, especially if they can use the same signal analyzer hardware. If we do a power spectrum on a vector signal analyzer with a fairly short time record, similar to the resolution we'd see on a swept analyzer in most cases, we see a measurement of this same spectral environment with some of the same limitations we saw before. Our probability of intercept is relatively low because only a small amount of the data a small percentage of the data is actually processed. But in vector signal analyzers, we can change that behavior to dramatically increase the probability of intercept, even if it's not to a very high percentage. And in this case, then, we're switching from about a 1,000-point FFT for this power spectrum measurement to a 100,000-point FFT, which, since we're using the general purpose processor inside the analyzer, this could be done about as fast as this narrower FFT. This much larger, 100 times greater FFT length or time record length means that we get a much larger probability of intercept. We get better frequency resolution, a better idea of the signal shape, and we get fine resolution and a lot of data about the magnitude or RF envelope of the signal. If we use the same technique, again, this is not a real-time analyzer, but a vector signal analyzer using a large number of points. If we use this same technique with a persistence spectrum capability, that is a persistence that's similar to what was available in analyzers many years ago as a storage oscilloscope tube. Using that and encoding by color, we start to be able to see some of the same things we can see with the real-time analyzer. So we're seeing signal spectral behavior with a much higher probability of intercept, though this probability of intercept may still be much less than 100%. So these are things you can do with the swept analyzer, or with the FFT or vector signal analyzers you may already have. A quick summary slide here if you are doing this kind of thing. Several steps that can get you a much better, higher probability of intercept view of the signal, and that is using much longer time records, as we've talked about. Typically numbers like 25,000 points or more. Our vector signal analyzers offer FFT lengths up to about 500,000 points. Narrowing the frequency span you're using to the minimum that's needed, that can reduce the sampling rate of the analyzer and get you closer to 100% POI. And then as appropriate, use things like Iaf Magnitude Trigger, pre and post delays, and things like pre-trigger delays in the vector signal analyzer. And of course we saw on the previous slide using the persistence or density or history displays. I'll show some examples of that here in the presentation. Of course, the other thing we can do with the vector signal analyzer now is to add a frequency mask trigger to our triggering capabilities along the same lines as the block diagram we talked about earlier. So in this case, we're taking digitized and filtered data from the digital IF of a signal analyzer. We're processing this with a couple of different kinds of triggering capability, and then either sending that into capture memory for post-processing or sending it directly into individual measurements. For quite a number of years in the vector signal analyzers, we've provided a magnitude trigger. That is a trigger based on the analyzer's, on the total amplitude of the signal coming to the analyzer's IF. The analyzer in real time taking the square root of I squared plus Q squared, that is calculating the magnitude of the signal in the analyzer's bandwidth, and doing triggering from there. That is not a spectrally sensitive trigger in the sense of a spectral mask. So it's magnitude of the signal in the analyzer's IF only. So it is not as sophisticated in terms of spectrum evaluation, but it has the benefit of being real-time and time-aligned. So the trigger is precisely time-aligned to the samples that cause that trigger to happen. The other type of triggering then is the power spectrum trigger. The real-time or frequency mask trigger has traditionally been in real-time signal analyzers. So a couple of examples of what that looks like. This is a screen actually using the frequency mask trigger in the vector signal analyzer. And in setting up that trigger, then we can set up, as you see on the lower display here, tabular or graphical data. We can set up high and low masks, and we can make up triggers based on the signal spectra itself. But the other type of trigger that's available in the vector signal analyzer is the magnitude trigger, where we're triggering only on the RF envelope of the signal. So the trade-off here is spectral sensitivity and selectivity versus in the frequency mask trigger versus time alignment in the magnitude trigger. So I'm talking a little bit here about vector signal analyzers as the complement to real-time analyzers, with real-time analyzers being exceptionally good at signal or signal behavior discovery. That is, finding signals or finding signal behavior. Once you've found that with the real-time analyzer, the vector signal analyzer, often operating on the same analysis platform, then allows for much more detailed analysis in terms of things like time domain, demodulation, analog or digital demodulation, and as I mentioned earlier, things like time capture and playback. This vector signal analyzer approach can be implemented in many different types of signal analyzer front ends, though I think most of the time for RF engineers will be using spectrum or signal analyzers. This can also be applied to multi-channel analysis, but we won't get a chance to talk very much about that today. Well, one of the best capabilities of the vector signal analyzer for Agile or signals or signal environments is signal capture. And this is a process where you do capture and post-processing. Upon a trigger or just upon a user pressing a button, you stream data into capture memory that's continuous with no gaps, and then do reprocessing of the data in a post-processing manner. You can start with using the existing center and span that you may have used from a swept spectrum analysis or from real-time analysis to discover the signal. And it's actually a very simple thing to do. Just press the red record button and then press play for playback. So the analyzer's defaults will often give you a good measurement. And this is one of the most useful capabilities in terms of producing insight and accurate, flexible measurements of these dynamic signals or signal environments. For an RF engineer, perhaps the most useful thing is that you can measure the same signal over and over again in real time with no gaps while you change analysis settings. I think we've all had the frustrating experience of measuring a dynamic signal or signal environment, changing our analyzer settings, seeing a different result, but not being sure if the different result was due to the change in our settings or because our signal changed in the meantime. So this is why time capture can be especially powerful. I'll show some other advantages of that approach in the slides to come. Earlier I mentioned overlap processing and the effects of FFT windowing. One of the advantages of time capture is that you can use virtually any overlap setting. Since you're processing gap-free recorded data, you can change overlap settings and essentially use that as a way to change the playback speed. So in this case, for example, 50% overlap produces a persistence display like this, 90% and 98% produce a much slower playback. This higher degree of overlap gives you better chances to analyze the signal without the effects of windowing. It gives you the chance to reanalyze the signal successively with high resolution in time and see how the signal changed over time. So the way that this works in the vector signal analyzer will, in most cases, will feel like a playback speed control. This time capture, this recording can also be used to more thoroughly analyze transients. So in this case, the time capture and playback are of the turn-on transient of a VHF radio. We're arranging the analysis displays here in terms of a spectrogram with the beginning event of the turn-on of the radio at the top and the end here. And see, we can see the frequency settling of the radio's synthesizer here. Since this is gap-free and since we have large and controllable amounts of overlap, we can see a lot of detail and we can see this in a vector mode that would not be possible in a real-time analyzer. We can see sidebands appear and disappear on this signal as it settles. We can see other detailed behavior, such as the final settling and lock of the synthesizer, and interestingly enough, a kind in the spectrogram, we can see a kind of a wide band splatter or burst of frequencies that happens around the time the synthesizer locks up. So this is low-level behavior that's subtle but may be important in the design of the dynamics of this synthesizer. So here again we're doing time capture, triggered in this case from the turn-on event, and then post-processing and playback with a lot of overlap to show a spectrogram. The spectrogram allows us also to identify any particular trace in the trace buffer. This buffer can be many thousands of traces deep. We can identify any particular trace in the buffer and then look at the spectrogram of that trace and measure it. Let's expand that or generalize that to the case study we've been talking about so far, and that is the 2.4 gigahertz ISM band. In this case, I've done a time capture over a period of about 25 milliseconds or so, more than one power line cycle, over a span of 100 megahertz, so the ISM band itself. We can see the relatively wide wireless LAN bursts here, here, and here, and we can also see two different wireless LAN users on the same channel that are sharing this channel. So we can see the wireless LAN users easily, and now we can also separate out the behavior of another user of this band, that is a Bluetooth, probably a telephone in this case, or headset. So we can see individual Bluetooth hops here, where time at the beginning is at the top of the screen, later time is at the bottom of the screen. And as a matter of fact, we can identify this same group of 5 Bluetooth hops, which start here, 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 and here. We can see that same group repeat here. Yes, that's the same group repeating here. So we can begin to pull apart the specific behavior of this frequency environment. One other prominent thing we can see in this environment are the wandering signals from microwave ovens. And just to make that clear, the microwave ovens operate on the power line cycle, 60 hertz here in the United States, or 16.7 milliseconds. So I set up markers that were that same distance apart in terms of time, and we can verify that these are microwave ovens going on and off once per cycle. Now we can see that those signals can be relatively powerful even at some distance because the microwave oscillators themselves are so powerful and the shielding is limited. And we can actually see some of that behavior that may be more troublesome here toward the bottom of the screen, where this microwave oven, when it turns on in this case, is actually sputtering across a wider band of frequencies. So there's a larger potential for interference here. Often these narrow microwave oven signals are not a problem for OFDM or spread spectrum signals as long as they're narrow band. But in some cases the microwave ovens are not nearly so well behaved. The benefit of this kind of view is that it gives you a comprehensive idea of what's happening over the entirety of this band over a particular frequency or time interval. And that interval can be relatively long, with captures available as long as hundreds and hundreds of megasamples. So this is a good way to switch from discovery of some of the occupants of a frequency band to extensive and exhaustive knowledge of just what's happening in that band, and including the dynamics. And you can imagine with more and more occupants of the band, you could end up with more interference. That interference in some cases can cause receivers to request retransmissions, which then further causes a larger occupancy of the band, and you can imagine how you would reach a kind of a cliff effect at some point where interference causes retransmission, which causes more interference, and you end up with a real problem operating the band. The time capture also in the Agile vector signal analyzers has another benefit for the RF engineer, and that is the ability to do something that you would normally do anyway with a swept analyzer, and that is to change the center frequency and the span. So with the vector signal analyzers, with an initial capture at a wider span, after capture you can change the analyzer's center frequency and span. So the ASICs and FPGAs in the analyzer do things such as digital filtering, resampling to change the sampling rate, and a digital local oscillator to change the center frequency. It's a fairly easy thing to do, just change the center frequency and span just as you would with a swept spectrum analyzer, and you can do that after capture but operate on the same data from a single capture. You can also select individual pieces of the signal in terms of time. So there is a window in the vector signal analyzer, a player, that has bars that can be clicked and dragged to the point that you want to analyze, or to the start and stop points that you want to analyze, and then you can actually drag the analysis point around within that. What this allows you to do is to do the kinds of things as an engineer you would normally do anyway, that is, select the frequency and time portion of the spectrum that you want to look at. By doing that, you can choose a piece of a capture, and in this case, for example, doing a Bluetooth demod of one hop from that entire time capture. In this case, we're doing a Bluetooth hop that has the potential from some wireless LAN interference, showing in this case the EVM and the spectrum. We could just as well identify and select a wireless LAN signal burst and measure how the Bluetooth hops affect the wireless LAN instead of the other way around. So this may seem like fairly advanced operation if you haven't used the vector signal analyzers before, but in reality it just means pressing the record button to capture a signal, and in playback doing the kinds of things that you'd want to do as an engineer anyway. That is, selecting a particular signal in frequency and in time using retuning or zooming or center frequency or span changes. And that can be then further used to do things like understanding adaptive equalization. So if you want to understand how the frequency transmission environment or the channel changes over the time of a capture, you can select individual bursts, and either in analog or gated sweep or in digital demodulation, you can examine this frequency response function. So for example, for an OFDM signal, by selecting one of the training sequences and looking at gated spectrum, you can trace out the frequency response function of the channel, or the channel frequency response. Or you can use digital demodulation, again on one of those same bursts, and the analyzer will provide the frequency response function for you directly. You can then select the individual burst or even the portion of the burst that you want for analysis. These are the kinds of steps you'd want to make if you're doing the kind of troubleshooting and optimization that often follows signal discovery. One other thing you may want to do in the real world of this kind of signal analysis, after you've captured a signal, often from real spectral environments, is to save away a piece of that signal. And again, because we can change center frequency and span and select start and stop points in the Agilent Vector Signal Analyzer, there are checkboxes to save the data, to save the captured data at the center frequency and span, the new data, and to save only the data between the playback start and stop times. So this allows you to find signals or signal behavior that are useful to you and then transport those to other tools. So signals captured in a signal analyzer with the VSA software can be passed along directly to signal generators to reproduce them as RF signals, or they can be passed along to analysis tools such as MATLAB or System View. Inside those tools, for example, you may have your own demodulator prototypes. So the idea here is to be able to follow your engineering instincts and desires after you've discovered signals and then captured them with tools such as the Vector Signal Analyzer. Let me go on briefly then to another case study showing some of the same types of characteristics but in a different environment. In this case, instead of a complex signal environment, it is a somewhat complex and agile signal. This is an S-band acquisition radar that's doing some scanning. It has relatively narrow pulses of about 6 microseconds each with a pulse repetition interval of 600 microseconds. So the duty cycle is relatively low here. The pulses come out in groups of 7 with a stepping frequency pattern of 10 megahertz. So stepping from low to high frequencies in 10 megahertz increments, 7 pulses, and then a gap before the repeating rate of 600 microseconds. So they're spanning minus 30 megahertz relative to the center frequency to plus 30 megahertz. And a real-time signal analyzer provides an excellent view of this signal, even though the duty cycle is relatively low. So with a very short acquisition interval, the analyzer can show you the 7 pulses across the frequency band. In this case, then, again, they're separated by 10 megahertz. But this is a succession of pulses. The low duty cycle is indicated by the blue color. Most of the time we can see at the bottom of the screen there is no signal present. A small percentage of that, then, one of the 7 pulses is there. So this provides a fast and a clear view of the signal, and it provides good intuitive feel for what's going on. If we look at this same signal using a swept spectrum analyzer, we can see why swept analyzers are not particularly good for measuring this kind of signal. In this case, we are only catching the signal intermittently. We have the dynamics of the signal interfering with the dynamics or combining with the dynamics of the swept spectrum analyzer to make it difficult to see the signal unless we use a rather long time of peak hold. Another problem that's not quite so clear is that this scanning antenna, as the antenna rotates, the amplitude varies over time. And since we're using peak search for a swept spectrum analyzer, we only catch the peak amplitude. So it's not a very productive way to look at this signal, much slower to acquire information, much lower probability of intercept. As I mentioned earlier on, the spectrogram is another way to use the real-time signals. In this case, then, the group of spectrums that come together to form a single spectrum update provides a view of the multi-tone signal on the top trace. The spectrogram then shows how the signal evolves over time. We can see the signal amplitude changing with intermittent peaks every few seconds. So a very challenging signal to measure because it's got a low duty cycle and it has one aspect of its behavior over time that has a fairly long time constant. That is, the repeat of the antenna rotation is on the order of 5 or 6 or 7 seconds. So there's multiple different kinds of dynamics going on here at once, though there's really only a single signal present. One thing we can do, as we mentioned earlier, is to choose a shorter acquisition time. This long acquisition time, where each spectral line is about 10,000 spectra of our 300,000 spectra per second, works well for showing the behavior over a long period of time, including the interval of the antenna scanning, but it doesn't show the individual pulses very well. We can improve that somewhat by going to a much more rapid acquisition time, and we can start to see not only the bright lines of the high intensity spectrum, the large amplitude pulses, but we can see some of the smaller pulses, and we begin to see those as small horizontal line segments here at the 7 different frequencies. So this gives us a little bit better insight into the time behavior of the signal. We have fine time resolution at the cost of a fairly short time window. However, that's an incomplete view of the signal, and we can do better if we're trying to do real signal engineering by using the vector signal analyzer and a time capture. In this case, the capture and playback gives us a lot of time resolution and overlap, and we can actually see 2 of the pulses here. We can also see the time envelope of the pulse. We could do gated sweep here, or even analog or demodulation. So again, here we're streaming the data rapidly into memory with no gaps, and then we're playing that back more slowly using a large amount of overlap. This reveals the individual pulses and their timing and amplitudes very accurately. This allows us to do the engineering and optimization we'd need to do for a radar signal such as this. This could be triggered by a frequency mass trigger or a magnitude trigger. Positive and negative triggers or delays are available with both of those. But since this signal is regularly repeating, we can simply do a time capture without trigger and see the same signal. However, if we do a longer playback, we use a lower value of overlap. We speed up the replay of the signal so that we can see all 7 of the pulses in one screen. We immediately see something that is troublesome, but that was, and it's obvious now, but it was hard to see in any of the other views. And that is that instead of starting with the signal that's 30 megahertz below the center frequency and then going to minus 20 megahertz, minus 10 megahertz at the center frequency, plus 10 megahertz, plus 20 megahertz, and plus 30 megahertz, we began our signal burst with the minus 20 megahertz signal instead of the minus 30 megahertz signal. So our pulse repeat sequence is wrong in this case. It ends with the minus 30 megahertz signal instead of beginning with this signal. And that's an easy error in signal construction to imagine if you actually place the interburst interval, the long interval, after the first pulse instead of before the first pulse, or after the first pulse instead of after the last pulse. So this is the kind of thing that's obvious in time capture and playback. It's very obscure in all of the other views, and it's the kind of thing that would not be obvious from spectrum, but would be a problem for a typical receiver. So of course, one of the points here is that defects or problems that are hidden in one view or mode can be obvious in another. One of the real benefits of time capture and the vector signal analysis is when you combine it with the real-time analyzer, using the real-time analyzer for discovery and using the vector signal analyzer for analysis, optimization, and troubleshooting. Of course, you can go on with the vector signal analysis there to do time domain or demodulation of the signal, gated sweep. You can adjust different window types to optimize resolution versus amplitude accuracy versus frequency and time resolution. So lots more there, more to do than we have time to cover this morning. But I wanted to summarize this kind of approach in discussing the kinds of tools you know how to use and some that you already have. And that is, it's an entirely reasonable thing to begin with a swept spectrum analyzer. They have the maximum flexibility in terms of frequency span, resolution bandwidth, and so on. They offer coverage of arbitrarily wide frequency spans. They have a familiar user interface, familiar displays. They're an excellent way to understand what's going on in most systems. But in systems where you have Agile and Elusive signals or complex signal environments, the real-time analyzers can offer some major benefits in terms of signal discovery. Finding elusive signals, understanding something about signal behavior, especially when signal behavior happens only on the order of seconds or minutes or hours. Using frequency mass triggers to monitor the spectrum and to trigger on particular spectral behavior. That also then offers a good way to spot unknown signals or signal behavior. In many cases, you know what's supposed to be happening in your signal or spectrum, and the biggest contribution you need to cause you to be able to sleep a little better at night is to know that you're familiar with everything that's happening in your signal band or with your signal in all of its different modes. But as I've discussed here today, the vector signal analyzer, software or hardware, is an excellent complement, with the real-time analyzer being a good tool for signal discovery, and for the vector signal analyzer being a tool for detailed signal analysis, including things like time domain and demodulation behavior, whether analog or digital, single or multiple channels, and then using things like signal capture and playback. Basically, find the signal you want, press the button to capture it, and then press the play button. Using this post-processing to examine the signal in very, very fine detail, and using this post-processing to process the signal for selection of individual signal elements and reuse, sending that signal on to other users. Let's see. And the point I want to make here is, in many cases, all of these analyzer types can be supported with a single signal analyzer platform, so that you can use a single tool and minimum number of user interfaces for all the different types of analysis. I have a couple of reference slides here toward the end of the presentation. I did want to provide kind of a reminder and reassurance that triggering can often be very helpful with Agile or Elusive signals. This triggering is available typically, well, they're available in swept analyzers to some degree, and in a greater extent in real-time and vector signal analyzers. This can give you a higher probability of intercept. It can allow you to measure the specifics you want and avoid measuring when no signal is present, or when none of the signals you want are there. And I wanted finally to discuss, or to summarize, two types of triggers that I have discussed in the presentation here this morning. I mentioned the Iaf Magnitude Trigger earlier. This was a real-time trigger, processing using ASICs or FPGAs to process all of the data of the analyzer in real time, but analyzing only signal magnitude to give a real-time calculation and trigger based on the total amplitude in the band in question, or in the span in question. This provides a particular benefit in terms of precise and repeatable time alignment for things like time averaging, which I don't really have time to cover today, but it's a powerful technique for improving signal or measurement performance. This also provides negative and positive trigger delays, which can allow you to see a signal that caused the trigger, to analyze behavior from before or after the trigger, and this is available with selectable level and polarity. Finally, if you're doing time captures, this magnitude trigger is actually available on captured signals. The other type of trigger I've talked about today is the frequency mass trigger, a more powerful trigger in some ways because of its ability to do real-time calculation of the signal spectrum and not only the signal magnitude, and to test that against positive or negative masks, to set different limits based on either the spectrum, build from the spectrum, or from a tabular set of limits. And this has one disadvantage in some trigger timing ambiguity. That is, your updates for triggers happen once per FFTs, so there's some limit to the time resolution of the trigger. It's not a trigger that's time aligned with the events in the spectrum. But it also offers some advanced trigger logic in terms of capturing individual signal behavior. Things like entering and leaving the mask can be good for synthesizer startup or shutdown or switching operations. And in Agilent's vector signal analyzers and real-time analyzers, this also is provided with negative and positive trigger delays. So that's the main points I wanted to cover in the presentation today. It's a bit shortened. The field is somewhat bigger than we have had a chance to discover in this limited time. But hopefully these two examples of Agile signals and signal environments, and the use of the swept analyzer tools, plus the real-time analyzer and vector signal analyzers, will give you some ideas how you can use these tools along with your own knowledge of your signal or system, and along with your own troubleshooting instincts and deductions to find answers, to discover signals, and to do the kind of engineering, troubleshooting, and optimization that's really vital in systems today. I provided several references here for more information. We'll be coming out with an application note as well on measuring Agile signals and these dynamic signal environments, covering lots of the points that I've done here today with quite a bit more detail, and a couple of technical overviews here. So thank you for your attention and attendance this morning. Let me hand this back to Allison.
Thank you, Ben, and thank you for your presentation. And now we'll get started with the Q&A session. So first question here, Is probability of intercept defined differently for wireless or general purpose than for surveillance?
Yes, generally speaking it is. What you'll find with the term probability of intercept is that it will mean different things to different users. Certainly for signal monitoring or surveillance operations, it means capturing and in many cases being able to demodulate any signal over a particular period of time in a band. For other general electrical engineering applications, especially in terms of things like wireless, it often means more the ability to capture the signals that you want, to capture the signal behavior that you want. And that does not always require what one would define as 100% probability of intercept. Though certainly if you want to understand everything that happened in a particular time interval, both the frequency mass trigger and the capture and playback capabilities of real-time analyzers and vector signal analyzers respectively can meet that need.
Okay, thank you. Next question. If you're demodulating two signals that are on the same frequency, maybe one is wide and one is narrow, can you always demodulate them both separately?
We kind of saw an example of that in the ISM band where if you had Bluetooth, for example, a Bluetooth hop interfering with a wireless LAN signal that was wider and longer, you could demodulate the Bluetooth hop inside the wireless LAN burst, or you could demodulate the wireless LAN burst and detect the influence or the interference of the Bluetooth hop. And that's done by setting the vector signal analyzer to the right center frequency and span and the settings, demodulation settings for each one of those. In general, you can demodulate either way. You can demodulate one inside the other, either the Bluetooth or the wireless LAN signal, even if they're at the same frequency and time. Although if there is enough interference, then one of those signals could cause the other one to fail demodulation. And that might be the kind of thing you'd be looking for. For example, you would want to know how those signals coexist and how much impact on modulation quality one has on the other. So as long as they're both comparable in amplitudes, in most cases you can demodulate one inside the other freely. If one is much larger or a combination of wider and more powerful, then it can be hard to demodulate the other signal.
Okay, thank you. Next question. Is there a disadvantage to capturing with the widest analyzer settings so you can analyze any narrower span later?
Well, it's certainly tempting when you're wanting to look at a particular frequency band to use a quite wide time capture setting. What that means then is the analyzer is sampling very quickly, so that means the time capture buffer, whatever its size, though it can be quite long, it will fill more quickly. Then when you go to narrower spans, say you're using a span that's 1/10 as wide as your capture, then each individual time record will be 10 times as long because you'll be resampling the data to a lower sample rate, and that means distilling down a large amount of data from the time capture for a smaller analysis bandwidth. So there is a trade-off and a disadvantage to sampling extremely wide in that you will consume your capture buffer length more quickly. So there is a trade-off there. Generally speaking, if you get a good understanding of the widest band that you care about, do that as a capture, and then do the post-capture tuning and zooming or center frequency and span changes. You'll be in good shape. If you find after capture and changing the span to a narrower value that you need a longer capture, then you can make a new capture with the longer burst. But if you only have one chance at a signal, then the deep time capture in the vector signal analyzers, even though it takes a while to go through that, it's worth doing the widest capture that makes sure to give you what you need.
Okay, good. Thank you. That's interesting. It sounds like it's all about trade-offs as usual.
Yes.
So it looks like that's all the time we have for questions today. I'd like to remind everyone about our survey. Agilent holds many free webcasts throughout the year, and we ask that you take a couple of minutes to complete the feedback form that will appear when you close the WebEx session. This enables us to deliver the content you need. Thanks again for your presentation today, Ben. And as we wrap up today's presentation, remember that we will email you a link when the on-demand version is ready to view, along with a copy of the slides. Thank you again for attending today's event. Analyze Agile or Elusive signals using real-time measurement and triggering, brought to you by Agilent Technologies. Please visit us at agilent.com/find/events for more details on our future webcasts. The copyright of this presentation material is owned by Agilent Technologies. I'm Allison Douglas. Thank you for joining us and have a great day.